So good day, everyone. My name is Nicolas Tranger. I work for Scality in the Paris office, and today I'll present you Untitled Kubernetes, which is a project we've been working on for about 2 years now, in which we use to deploy storage solutions. First, very short thing about Scality. Who are we? What do we do? We build scale-out storage, both file as well as object. I have a bunch of customers all over the place in various markets and like 5 or 10 different verticals. Been around for roughly 10 years now. Maybe a little overview of what this presentation will be like. Start with basically our journey towards Kubernetes. Why did we eventually, or in the end, pick Kubernetes as the solution to deploy our software? How did we get there? What are the benefits we expect from it? Then a bit about Untitled Kubernetes itself. What is it? What does it do? The first iteration we went through, then the second iteration we're currently working on. And finally, a bit of an outlook into the next things we will work on. So the history, or how we end up with Kubernetes, really aligns very well with the various products we have as well. Scality Ring was the first product. It's an on-premise distributed storage and file solution, object storage and file solution, which we, in general, run on physical machines. Sometimes, or parts of the architecture can be in VMs as well. This is fully software defined, so we expect the customer to have hardware available, or we work with partners to provide this hardware. And the only thing we can rely on is an operating system. Very often this is Red Hat or CentOS. We also support Ubuntu. And the resource pools here, they're fairly static. A customer buys 6 servers, buys 12 servers, maybe at a later point in time add 6 more servers, but it doesn't change every single day. Procurement of new servers and getting them racked in your data center and whatnot takes a while. In this solution, the roles of the various servers, they're rather static as well. You're a storage server, or you are a front end where there's an NFS server running or whatnot. And this whole thing is deployed using system packages, RPMs, DEBs, using SaltStack, which is a configuration management system and automation system, a bit like Ansible or Chef or Puppet or all the others that exist. And as mentioned before, the system, once deployed, is relatively static. Also, given what it provides, storage tends to be not a bunch of services that change all of the time. Then a couple of years ago, we started implementing a new service, or a new part of the product called the S3 connector, which gives S3 compatible access to the storage system, the object storage at least. Again, this runs on physical servers, sometimes in VMs, fairly static as well, but we took a different approach when it comes to the software architecture here. We started using microservices, and instead of distributing this as system packages, we embrace Docker and the container model, so all the services that make up the S3 connector are running as Docker containers. And we use an Ansible playbook, or a bunch of Ansible playbooks, to deploy these containers on the various machines that make up your cluster. There is no runtime orchestration. What I mean with that is the way Ansible works is you specify a certain set of steps that need to be taken to deploy your solution. You run this. Ansible in general runs over SSH, and once the deployment has succeeded, or failed for that matter, that's the end of the story. There is no active component running in your cluster. Unlike in SaltStack, there is an active component running in your cluster, and we'll get back to that later. We also integrated a whole bunch of extra services like log management and monitoring as part of S3 connectors, such that our operational people, or your operational people, can manage the system over time. Then about 2 years and a half ago, we started working on this new thing called Zenko. It's not a storage solution by itself, but it's a so-called multi-cloud data controller, which allows you to send data to various clouds, sync it between those clouds like S3 or Microsoft Azure Blob Store or whatever else. And unlike Ring and S3 connector, which are built for on-premise deployments, Zenko was from the beginning architected to potentially run in the cloud. So run on AWS or on Azure or whatever, which for us was quite a big paradigm shift, going from on-prem data centers to virtual machines, or mostly virtual machines in the cloud is quite a change, which brought many new challenges, but also quite some new opportunities, of course. My colleague Vianney did a talk yesterday about Zenko, so if you're interested in that project or product, please take a look at his talk. The deployment of Zenko was based on the deployment of S3 connector, where we use containers for all the services. Some of those are even shared, because Zenko also speaks S3, the protocol. So we have an implementation of S3 that is shared between the connector as well as Zenko. And we decided to start using Kubernetes to deploy these containers on your servers or in the cloud when you're using EKS or AKS or GKE or any of the hosted Kubernetes offerings. But we still need to be able to run this on-premise as well, so you need an on-prem Kubernetes cluster to deploy Zenko. Some of the benefits we saw from doing this, instead of continuing to use SaltStack or Ansible to deploy these containers, is that it's homogeneous between both in the cloud as well as on-premise installations, because in the end, Kubernetes, if you want to call yourself Kubernetes, you need to be conforming to a whole bunch of tests that the CNCF publishes. So the platform is always the same. There's a lot of services that are provided by Kubernetes, services or functionality, which we otherwise need to build ourselves. There's networking abstractions and policies you can apply to the network. Things like service restarts. That seems to be fairly simple, but even implementing rolling upgrades across hundreds of nodes is non-trivial to do yourself. Things like log capturing, service monitoring, load balancing, TLS termination are all kinds of things that are not core to our business, core to our product, but are still required. So you can let Kubernetes or services running as part of Kubernetes take care of this. And it allows for more flexible resource management. So especially when you're in the cloud, adding more VMs when the load goes up, or either expected or unexpected, removing those when the load goes down again. Those machines need to be added to the cluster, your services need to be deployed in this, etc. This is the things where Kubernetes shines and where Kubernetes will take care of all of this. For the deployment, let's assume we have a Kubernetes cluster, but that's actually what the topic of this talk will be about. Of Zenko, we are currently using a Helm chart, which is kind of a templating engine, which allows you to create YAML manifests to describe the objects you want to run in the cluster. We've been working with the open source community a lot throughout both the Zenko project as definitely also the Metal Kubernetes project. We use a couple of charts that are provided by the community. We've been contributing patches. We became a maintainer of some of those. In the next generation of Zenko, we will no longer use a Helm chart, which is again fairly static, but we will also use a so-called operator, which is an application that runs in your cluster and takes care of the life cycle of your actual application. So it's not an application, it's a service. Your operator will create all the objects, will make sure that all your containers are spawned or will be spawned by Kubernetes. When you want to upgrade and it's a multi-step upgrade scenario, then it's the operator who needs to take care of all of this. It's a bit like a human operator, but then fully automated. If you want to try this and you have an existing Kubernetes cluster, it's fairly easy to set up. There's a link over there, and we have for tests, well, I mean, not our tests, but if someone wants to test this, you can also go to the website that's at the bottom of this slide to basically get an instance of Zenko hosted by us for trial purposes. What is Kubernetes? I guess most people already kind of know. really don't know what to expect here. It's primarily a container orchestration system, or at least that's how it's positioned. But what is the core of Kubernetes? It's basically a database with an API on top, where in that database you describe the desired reality of your system. You say, I want to run 5 instances of this container, and then there's other tooling part of the stack that will make sure that at any point in time you will have 5 instances of that container running somewhere in your cluster. All of that is available through well-specified RESTful APIs. There's a whole bunch of authentication and authorization with role-based access control in there. And then Kubernetes comes with a whole bunch of controllers, so operators, controllers. It's somewhat of the same thing, that take high-level objects like I want this service and I want 5 instances of it, and refines it into either the physical reality you want, 5 container objects, or even intermediate layers where this high-level object will create a slightly less high-level object that then will be further refined into what the reality should be. Next to that, there's a couple of services that run on the physical or virtual machines that make up your cluster, and ensure that containers get started, for example, or restarted or monitored. And a set of APIs or plugins, and the previous talk went into that quite a bit, to interact with the system. So there's CRI, which is a container runtime interface, which abstracts over, for example, Docker or Cryo, or in the past, Racket. There is CNI, which is a container networking interface, which allows you to set up the networking required to have all your containers to be able to talk to each other. There is CSI, that was explained before, which is the storage interface, which allows you to provision, attach, mount, unmount storage volumes. So in essence, containers are really only a small part of what makes up Kubernetes. Obviously, at runtime, everything is a container, but Kubernetes goes way beyond running containers. And then a bit of detail. What is the unit of scheduling in Kubernetes? It's actually not a container, but it's a so-called pod. What is a pod? It is a set of containers that sit in the same networking namespace, and potentially also other namespaces. Where networking namespace, I mean the Linux concept of network namespace. Why is that the case? And you're not scheduling one container at a time. It's for the sidecars that were mentioned before, where you want to have a pod is more like a virtual machine in a sense, where you can have multiple services in a single pod if you want them to live together. Where one service can then, for example, provide monitoring of the other one that's sitting in the same pod. And pods can request attachments to persistent storage, and I'll have a little bit more about persistent storage as well, or persistent storage in Kubernetes later. So, Metal Kubernetes. For initially Zenko, but now also for all the other software we are developing in the next generation of our product, we are using Kubernetes. It still runs on-premise, so we can't really expect the customer to have that up and running. We already expect them to have servers and a base operating system, but Kubernetes is quite a different beast. So we started looking in the various offerings of on-premise Kubernetes, and now I'm talking 2017, that we could integrate or rely on as part of our offering, but most of them did not really suit our needs, or at least the needs of our enterprise customers. Again, back then, there were a lot of solutions that allowed you to install Kubernetes on EC2 VMs, for example, or expected to have only a single network available, or be online, which for our customers is often not the case. We need to be able to install this whole thing in a fully air-gapped environment. So in the end, we decided to roll our own, and we got a small team to build all of that. That was the Metal Kubernetes 1.x. And we used this as like the tagline of the project, and I'll go into the various parts of it in just a second. So Metal Kubernetes is an opinionated Kubernetes distribution with a focus on long-term on-premise deployments, unlike many of the other offerings. It's opinionated because we don't really allow you much choice. in the end, our customers, they're not buying Kubernetes. They don't care about, I can use this CNI or that CNI or even another one. We have to make that choice for them. And we made it. We use Calico. And that's just it. It's long-term. Storage is quite mission-critical, so we can't just spawn up a new cluster to deploy a new version of the software. This is not something where you just change your cluster every couple of weeks or months. Once it's been deployed, and then later on it will be upgraded or downgraded, etc., it needs to be running for years and years in a row. And well, it's on premise, so we basically don't expect anything to be available, except again, hardware and basic operating system, even though that may even change. First iteration of all of this was Metalgate 1.x in the scope of 3 to roughly 20 physical machines. We don't aim for clusters of hundreds or even thousands of machines, even though Kubernetes supports this, but it's not something we need. So it may work, it may not work. Where those machines are pre-provisioned by the customer. We did use an existing Ansible playbook called Kubespray to deploy this cluster, or at least the very basics of the cluster. So we use it to deploy the control plane. And I'm not going into the architecture of Kubernetes itself, but in the previous talk there was one slide where you had a control plane and then the workload plane. So we use Kubespray to deploy this control plane. We also use it to deploy etcd, which is the highly available database that Kubernetes uses to store all the information it needs to store. And to deploy CNI, so to deploy Calico, which is kind of a software-defined networking solution. We added on top of stock Kubespray a lot of static and dynamic inventory checks, operating system tuning, operating system security, all of this based on the experience we have with deploying all of this as part of Ring. So it doesn't really change whether you are deploying your product as RPMs on a Red Hat system or you are deploying Kubernetes as not necessarily RPMs but still on the Red Hat system. To a certain extent, the level of security measures you want to take in the system are the same. And then we added a whole bunch of operational tooling, so-called ingress controller, which is basically an Nginx which runs on your various servers and allows access to the HTTP services that you run inside of the cluster, and some others, and I have a couple of screenshots of those. Oh, actually I forgot, I was going to do a demo. Do you want a demo? Like a live deployment of Metalgate 2.x. Maybe I'm too late now, but anyway. So I'm going to run this in a virtual machine on my laptop here using Vagrant. And to be very certain that I'm not pulling any tricks, I'm going to restore this virtual machine to a very, very base CentOS 7 image without anything pre-installed, which will take a couple of seconds, and then I can start the deployment. Right, and then finally, we also need to take care of storage because, well, storage is what we do, and all the services that we deploy need storage. No, not all of them. The stateless ones don't need storage, of course. Those cluster services, what am I referring to here? It's not necessarily stuff that we build. In the open source world, there's a whole bunch of operational tooling, etc. available. So we take that, we integrate it, and we contribute wherever possible. So we use Heapster. It's a Kubernetes tool to capture metrics from containers. We use Metric Server, which is kind of similar, and nowadays Heapster no longer exists, actually. We use Nginx and its ingress controller for ingress and TLS ingress of HTTP services and TLS termination. Prometheus, the Prometheus operator by CoreOS, now Red Hat, now IBM, to deploy Prometheus and Alert Manager with it, a whole bunch of dashboards, the node exporter to get Linux-level metrics from the system, ElasticSearch, Curator, FluentBit, Kibana to get logs aggregated centrally so your operational people can get into the logs that come in from all of the system. And really we want to give a great out-of-the-box experience for operators, where if you deploy, for example, Kubespray as is, you're on your own. There is no operational tooling foreseen. Maybe I can start this one in the meantime. So I have my VM running, and we will start the deployment. Okay, so here we are using a tool called DoIt, which is like make or other build systems. I did build the thing up front because it will download a whole bunch of containers and RPM packages and whatnot from the internet, which wouldn't work live. And then it goes out, SSHs into my VM, or Vagrant does that, and it starts what we call a bootstrap script, which will deploy actually a single node Kubernetes cluster in this one VM. The architecture we work with is you start from one node, we call that a bootstrap node, and then you can add more nodes to your cluster, and those can be control plane nodes or workload plane nodes, or nodes that do both at the same time. I can show you what's going on here. Oops. So, do it again. We have basically the script calling into salt to do the whole thing. And let's cross fingers that it succeeds. So, the tooling we integrated in Metal Case 1 was the Kubernetes dashboard, which you have here, which is a web interface to manage your cluster. Kibana for log access, Prometheus and Grafana for metrics. That's basically it. A very short interlude to go into storage in Kubernetes. In Kubernetes, just like, as was mentioned before, there's CSI to provision storage, and in general, the project tries to not tie itself into particular implementations. So storage in Kubernetes, it can be file, it can be block, it can be local disks, it can be an attached SAN, it can be an attached NAS, whatever. The data model itself is fairly simple, maybe too simple, and it all starts with a so-called storage class. A storage class is an object that describes storage volumes of a particular class, obviously, and also how volumes of this class ought to be deployed. And this is where, for example, CSI comes in. In the storage class, you can say use the CSI driver to deploy a volume of the storage class. Secondly, there is a so-called persistent volume, which is an object that describes an available volume and how to attach to it and or mount it. And it's part of a particular storage class. And then finally, a persistent volume claim, or PVC, is an object which links a pod to a persistent volume. So you can have in your cluster a set of available persistent volumes, pre-provisioned or even provisioned dynamically on request when a new PVC comes up. And a PVC literally claims a PV, says this is now being used by a certain workload and no one else can claim it. So in classic on-demand provisioning, what happens is a user or an application or an operator creates a PVC and says, I want to claim persistent volume of a particular storage class. If there is no PV available in that storage class, and according to whatever rules the PVC specifies, like I want to get a volume that's 1 terabyte in size, then the provisioner that is configured in the storage class will come in and it will do whatever it takes to provision such volume and then create a PV at the end. Now this PV is available and then the PVC can be bound to the PV. If you have if you have manually created PVs in your cluster before, then this provisioning doesn't need to happen because the PVC can be bound immediately. And then CSI, well, as I said before, the previous talk went into this, so CSI is really about extracting how to attach and mount volumes or even create volumes from the core of Kubernetes, which today is all managed within the project itself. Let's take a look. This is still going on? Okay. So storage in Metal 1, we are running on-premise, not in the cloud. So we don't have Elastic Block Storage or any of the other storage platforms that you find in the traditional clouds. We can't really rely on a NAS or a SAN to be available because, as I said before, we build storage. Like not a prerequisite we can have. And in the end, we end up with the lowest common denominator between all of this, which is local disks in a system, which is fine because we're pretty good at managing those. In Metal 1, we decided to statically provision PVs at installation time. We use LVM to slice up your disks into various partitions, format them, expose those as PVs to the various workloads, and that's basically it. It's very static after deployment, and we didn't really need much more than that for Zenko deployment. Now that is changing with the next generation products. So second half 2018, we started to realize that the path we took in the beginning using Kubespray was not going to fly in the future. So we ran into a couple of roadblocks based on missing features that were difficult to add, whatnot. So basically, because of this list and especially what's in that link, we decided to kind of restart from scratch. We also grew the team quite a bit, going from 3 to roughly 10 people. And then was Metalgates 2 born, which is the platform, we literally call it the platform internally, for our next generation products. Let's take another look here. So this is almost done. So we changed the approach of the project, where Metal 1 was really about a general purpose Kubernetes deployment system based on Kubespray. Metal 2 is slightly different. You can still use it as a general purpose Kubernetes deployment system if you want to. At the same time, we really see it as a vehicle that we include in our product, or that others can include as well, and the architecture definitely allows this. So if you think that for your product, whether it's a storage product or something completely different, Kubernetes as a platform makes sense and it needs to run on-premise, then you should really be able to take Metal 2, ideally contribute back, and use it as a part of your product, as your offering, instead of saying, 1, we deploy Kubernetes, 2, I deploy my project or my product on top of it. So this is kind of the architecture, where at the bottom you have those 2 gray boxes, and that is Metalgates itself. There is actually only one service that runs as a standard system daemon on all the nodes. It's that salt minion on the lower left corner. Everything else is containerized. So our salt master itself, we run it as a container. etcd is containerized. The whole Kubernetes control plane is containerized. Everything else we run as part of the stack, like Prometheus and Alert Manager, the ingress, custom UI we built, and I'll show that later. The storage operator, which is also something new, and I'll go into that. All those other services, everything is containerized and comes up after you deployed the system. And then we came up with this thing called solutions, and they are the green, blue boxes on top. So this is where you integrate your product with the Metalgates platform. Every solution in itself is a self-standing application that comes with everything required to run it, including offline images of the containers, its own UI, its own operator, etc., etc. So we have a solution for Zenko. You can just drop that in. It's kind of, from a Metalgates point of view, it's like a marketplace where you include multiple solutions in the system, and then from the UI you can say, click, I want to get a new instance of Zenko, and a couple of minutes later you should have it. We are working on this middle box, which is our next generation storage product, but I can't really talk about that too much. And then there could be others as well. Maybe it's ours, maybe it's your product, whatever. And in a sense, this relates a bit to the CNCF CNAB, which is a cloud native application bundle. It's a bundle of everything you need to run an application on Kubernetes. So we are no longer building this on Kubespray. Oops. That's not good. Let me rerun that. Anyway. We built it from scratch, and the resulting cluster is kind of isomorphic to a kubeadm deployed cluster. What is kubeadm? It's the Kubernetes project to deploy Kubernetes clusters. We didn't use that for a variety of reasons, but we do take the same approach, and actually, from the Kubernetes project point of view, all the systems that deploy Kubernetes are supposed to kind of use the same approach as what kubeadm does. We don't want to use one of playbooks where you say install and then cross fingers that it keeps running for the rest of the lifetime of the solution. We do focus a lot on day one or day n operations rather than only day 0, which is when the thing would be installed. We are using SaltStack, so we get a dynamic system, which means that we can react inside the cluster to various events that may happen. Nodes can go down, of course, and we could do something about that, potentially. But there's even more mundane things, like you will very often see reports on a mailing list of, I had my cluster running for a year, and now it's all broken, and in the end, it turns out that the cluster was deployed with TLS certificates of an expiration date 1 year after that cluster was deployed. That 1 year is reached and the whole thing blows up. Because we have a dynamic system, we can, we actually have things in place which will check the validity of certificates. And if at a certain point in time, like 7 days before their expiration, we detect this, we will rerun the states that will regenerate or recreate new certificates, restart the services that use them, etc., etc. And we also need this because we need to be able to interact with the system from inside Kubernetes. And this is mainly related to the storage provisioning, which I'll mention later, as well as upgrade and downgrade of the cluster itself. We don't want to have some administrator go out and from his laptop run something to upgrade a 100 node cluster in his data center. So as I said, we are using SaltStack. It's dynamic. There's a master node that's always present. And one other reason to use SaltStack is we've been using it for many, many years now. So our developers, our technical services people, they all know it quite well. So good reason to stick to what you know. We build everything into a single ISO image. The reason for this is, again, offline deployments, so that ISO comes with all the offline container images, RPMs that are needed, whatnot. And the deployment of a cluster is as follows. You start with this bootstrap node, you mount the ISO, you create a very small configuration file which describes the various networks you have. For example, if you have a physical control plane network and a physical workload plane network, then we want to know like which CIDR is to be used for one and which CIDR is to be used for the other. We try not to use shell scripts, etc., wherever possible. So we kickstart from batch into Salt as soon as possible. In local mode, we deploy the master node. We then deploy the minion. Then start using that master node, and we end up with a 1-node Kubernetes cluster. We are currently using Containerd as a CRI, not using Docker. Despite in Metal 1, we are using Docker. And we have been looking into Cryo instead of Containerd, maybe someday. It doesn't really make that much of a difference anyway. As a CNI, we stick with Calico, which is the overlay network. And then once you've been bootstrapped, you have this fully functional 1-node cluster. You can add new nodes by either creating a new node object in the Kubernetes API with a couple of annotations about how can I SSH into this node to bootstrap its provisioning. Or you can do it through a CLI or through a UI. As I said before, we have built our own UI for all of this. And then these nodes can be either a control plane node or an infra node, where infra means it runs Prometheus, it runs Core DNS, it runs infrastructural services that you may not want to collocate with your actual application nodes. But all of this is optional, or it's a workload plane node, or you can mix and match those as well. And then the cluster upgrades and downgrades is fully automated. You basically come up with a new ISO next to the existing one. You say, platform, here is a new ISO, I import it in the platform, and then we have a fairly simple script to basically say, upgrade my cluster, 1 node at a time, starting with the control plane, then the workload plane, to this new version. May not be very useful, but since we want everything to be available offline, we also need to have a so-called Docker registry available offline, which serves the container images to the various nodes. We started by including the official Docker registry as part of this solution, but the Docker registry itself, it allows you to push images into it, and it has access control lists, and I don't know what. It's a rather big server. Whereas in the end, all we want to be able to do is is to pull images from this central Bootstrap node, like a Yum repository in a sense. But I couldn't really find anything that suited our need. One reason why we wanted not to deploy Docker registry is because we already have an Nginx running to serve all the Yum repositories, the RPM repositories. So I built this thing that basically you give it a bunch of Docker or container images. It will generate an Nginx configuration which emulates the API of a Docker registry up to a certain level, but a certain level that's good enough such that Docker, Containerd, Cryo, Scopio, and other tools are very happy with that, and you can just serve your images using a plain Nginx instead of running yet another service next to it. So everything in this new architecture is centered around Kubernetes. We use that as a source of truth. We don't have any other place where we keep track of which node make up the cluster, etc. So the nodes themselves, the node objects in Kubernetes, form the inventory. The roles of the nodes are set as labels on those node objects, and that is, again, the source of truth. We run a whole bunch of cluster services that we need for deployment, like the Yum registry, repository, or the container registry as kubelet managed pods. So they are, if you ask the system for, give me a list of all the containers that, or the pods that run in my cluster, give me the logs, give me metrics about them, there's no difference whether it's an application container or it's one that makes up the cluster. And in the end, it's all relatively stateless because all the state sits in etcd. So as long as your etcd cluster is up and running, then all is good. We do have some scripting, of course, to back up and recover in case of disaster your etcd cluster and the rest of the cluster. And all of this is API driven and API first. So we try not to do anything that goes beyond or besides an API. We have the Kubernetes API, of course, and then we have Salt API to interact with the systems themselves, the host operating system. We integrate Salt API authentication with Kubernetes authentication. So if you have an authentication token for the Kubernetes API server, you can pass it to Salt API, and Salt API will then validate whether it's correct or not. The same for authorization. We map your Kubernetes user and certain access it may or may not have into Salt groups. And based on that, you can or cannot call certain Salt API operations. And this works really well because in Kubernetes you also have this concept of service accounts, which are not users that interact with the system, but services that interact with the system and still need to authenticate toward the Kubernetes API. So there are service accounts, they get their own token, and we have at least one service which needs to talk to Salt, which is the storage provisioning operator. So in general, we embrace a Kubernetes model of you first declare what you want, and then there is some system somewhere that will realize what you want. So 100% offline installation. We covered networking. We make a distinction between the various networks, physical networks that your servers may live in, which is one of the reasons why the existing solutions did not fly for us. They kind of assume one flat network. We use keep-alive-D for a highly available control plane, but you can also use an external virtual IP management or load balancing solution if you want. All of this running on currently RHEL 7, CentOS 7. We have patches coming in to be able to deploy on Ubuntu 18.4 LTS. And of course, we're looking forward to get all of this to run on RHEL 8, CentOS 8 as well, but we have not started that work yet. We integrate optionally with your enterprise authentication and authorization systems. Can be an LDAP service or Microsoft Active Directory or whatever else you may have in place. We have our own cluster management UI, and we really focus on real hardware. So when it comes to monitoring, for example, we include things like smart monitoring or ILO or whatever the other vendors may have, rather than only look at what you would see in a virtual machine. So this is that UI. I wish I could show it. Ah, no, it succeeded. Let's do a live one. I'll copy my credentials to my local machine. Okay, so I have one node in my one node cluster that has the roles bootstrap, etcd, infra, and master. And we're currently running Kubernetes 1.15. Version-wise, this is Metal Kubernetes 2.4, and we stick the minor version with a version of Kubernetes. It's not the same, but so Kubernetes Metalcades 2.0 is Kubernetes 1.11, and then 2.1 is 1.12, etc., etc., etc. So we have these nodes. I can show you what is running in the cluster. Oops, let me. So we have a bunch of services that are now running in the cluster, and I want to access the UI, which is currently exposed as a node port. That's not great, but we're working on it. Need to know the IP address, 45, and port 3936. 30. Oh, is it right? Okay. A little trick, because the UI itself is a client-side application, pure JavaScript, React, which interacts with the two APIs. Those APIs are exposed over TLS, but I'm using a self-signed certificate, so I first have to tell my browser, yes, you can talk to this service. We're going to change that as well, but priorities. So I need to do it both for the Kubernetes API as well as for Salt API, okay. Oops, yes, all good. So here's my cluster, which is currently over-provisioned because there's only one node. I can look into my nodes, there's volumes. I can show which pods are running there. This is rather basic, but that's also the intent, because this being part of our product, we don't want to expose the complexity of Kubernetes to our customers. So Kubernetes is really an implementation detail of this whole thing, which is why we're not simply using the upstream Kubernetes dashboard and then tell a customer, use this, because they'd get lost in it. So that's the UI. Yeah, I could add another node, but we'll run out of time, so I'll skip that. Although I can show it. If I want to add a new node, all you have to provide is a name for it. Say, yeah, which roles you want to assign to it, how to SSH into the node to bootstrap the whole thing. Then you click create, then you click deploy, and you're good to go. So that's the same. So storage provisioning. We still focus on local disk manipulation because, again, we build this storage product. But unlike Metal 1, LVM does not really suit our application needs, because now where Zenko itself, it uses things like MongoDB, Kafka, whatnot, which you can run on partitions. The next generation products, they build the actual storage layer. So we want to get 100% of the performance you can get out of an NVMe drive or out of a spinning disk or whatnot. So we don't want to add device mapper layers on top of it, etc. As said before, we embrace this Kubernetes model and Salt. So what we do is we came up with a so-called custom resource definition, which is the extensibility part of the Kubernetes API. And we created a new kind of object that you can store in that API called volume. And then we have an operator which runs in your cluster. It's one of the pods that you can see in here. Our storage operator right there. So we have one instance of it running, which will see when you create a new volume custom resource. It will see this. In the custom resource, you kind of describe what that volume should look like. Every volume has a storage class. In the storage class, you say what the file system should be, what the MKFS option should be, how the disk itself should be accessed, what the mount options should be. And then the storage operator, and this is where the service accounts come in, it will talk to Salt API to realize this. So what we'll do is currently we have only two types of storage, which is a raw block device or sparse loop device, where sparse loop device is really useful for testing, but definitely not for production. And raw block device is basically you have an existing /dev/whatever node on your host. We are in the process of, so as part of Scality Ring, we have a lot of automation to set up RAID controllers, to attach disks to those RAID controllers, whatnot. We are in the process of integrating this in Metal 2. So you can create a volume and you can say, I want these drives on these lanes to be connected to this RAID controller using this RAID level and whatnot. You post this into the API, and then potentially a couple of minutes later, because file system creation on a multi-terabyte disk can take quite a while, this will be done, and then once the physical volume has been created, formatted, etc. Through Salt, we create a according persistent volume object in the Kubernetes API, and from that point on, a PVC combined to it, and that's the standard Kubernetes way of doing things. We are not using CSI for a couple of reasons. The main one being that the CSI model, at least from my point of view, works really well for dynamic on-demand provisioning. Like create a new EBS volume and then it will be created for you and it will be attached and whatnot. We don't have that. There's only this number of disks you have in a server, and if a user wants a new disk, well, it's not there. So instead we have the operator, the person managing the cluster, basically saying, here are the disks. I created them as volume objects. They end up as PVs, and then you can bind to them. But that's it. There is no dynamic provisioning, because it'd be great to be able to dynamically provision a new disk in a server, but physical reality prohibits that. So this is in the UI, and I can also show the actual UI. Sure.
Can you clarify so the discovery of the hardware devices of the disks, the operator, like the human, needs to take action to tell the system about it, or the system will discover and claim them all?
So, a very good question. The question was discovery of those devices. How do we handle it? Right now, in the implementation, you have to say what you want. We don't do any discovery. However, in Ring, we do discovery. So we have the code available to perform discovery and then potentially create the according volume objects automatically. We haven't included that yet. So this is a list of the volumes that exist on this particular node, because unlike in general in Kubernetes you use attached storage, so storage is not attached to a particular node. In our case, because it's disks that sit in a node, we tie those together. You can take a look at what's their size. In the test environment we use sparse loop devices, and you can create a new volume. I can say I want to get my volume foo in the storage class metal case Prometheus, sparse loop device of say a terabyte. It's sparse anyway. So now I created this object. I could show it here. There's my object called foo. If I look at what the actual object, then you can see it's a sparse loop device. I want 1 terabyte roughly of size, and I use storage class metal case Prometheus, which, as I said before, specifies, among other things, the file system creation options and the file system that needs to be used on that volume, etc., etc. And now, if all goes well, I should get the actual PV. So this is the Kubernetes concept of a persistent volume that now exists and is available to the workloads. You see it's available. The other two are already bound to a PVC that is used by a pod that then runs Alert Manager or Prometheus. This one. So, yeah. Oops. Then we have monitoring. I can show you the Grafanas. Oops. Nope. No. That's better. We have a whole bunch of dashboards. Again, we will add custom dashboards, but these we didn't build them. They're available from open source repositories. And the one I wanted to show was the one for persistent volumes. So, no, I don't have 7 days of stats. Here we can see the persistent volumes and their consumption. We also have rather detailed node-specific dashboards where you can also get details about your file systems or about your disks, but this is just a vagrant VM, so it's not very useful. Whole bunch of stats. Disk temperatures using Smart that we saw. And then finally, deploying solutions. So the cluster itself for us is not the end goal. A solution is your application, which again needs to be built as an ISO because everything needs to be available offline. A solution itself is built around an operator, so every solution comes with its operator to deploy it, upgrade it, manage it over time. ISO images, we mentioned, they're imported in the cluster, which means that the containers are added to the registry that we have available offline. We deploy your operator and the custom UI that comes with your application, and that UI can do whatever it needs to do. And also create a solution-specific storage classes. So as I said before, our next generation storage product will use those local disks, and there we specify I want to use XFS with these particular formatting options and these particular mounting options. So in a sense, these solutions form the marketplace application store of your cluster, and then a user can create new instances of your application. That's basically it. And then, unlike Metal 1, where the Prometheus that is shipped as part of it is used to only monitor the cluster, in the Metal 2 scenario, the Prometheus and all the other services that come with the cluster are also meant to monitor your application workloads. So I showed the Grafana before. The intent is really to have in a single Grafana both the dashboards for the Kubernetes cluster as well as the dashboards for your application or other applications that run into in that cluster. And a solution itself can just create a new Grafana dashboard object in the Kubernetes cluster, and then we include it in the Grafana. So a quick start, if you want to try all of this out, download it and run Vagrant up, and that should be it, except for a couple of dependencies that we need in the build process. And then moving forward, what we want to add again is log aggregation, add more documentation because, admit it, that is a bit lacking, improve the UI further, device discovery, as was asked before, where maybe Swordfish can be used, need to be investigated. Support non-traditional device access like networking with SPDK or storage with SPDK or DPDK for networking, add tracing capabilities, whatnot, and then eventually even do PXE boot of new systems, so we don't even need an operating system on the servers of the customers. And I'm out of time. Luckily, that was it. Thank you.